Here's a teeter-totter. We're going to talk about static equilibrium and a lot about torque and gravitational torque. So each of these children have a gravitational torque that's downwards around this pivot. I do also want to show this rather busy slide about the test, because the test is marked. So sorry for all this information dump, but all of this information has already been delivered by the portal, either with, if you click on My Grades and then go under the item statistics, it'll tell you what the statistics are for things. So this is, for example, the statistics for test 1, and this is actually for all the students who are still in the course. And there's the histogram. Test 1, average was 74%, median was 79%, and if you bin it, so that means so half of you got more than 79%, half of you got less than 79. The mode depends on how you bin it, but if you bin it by 10%, as I've done here, then actually the bin that has the highest number of students in it, which is the mode, is the 90 to 100, and so the mode was 95% on test 1. So this is a very strange looking histogram for U of T, I think. Test 2, on the other hand, average was 62, median was 61, mode is 65, and also the number of perfect scores went down from 67 to 8. Anyway, this is a much more sort of typical looking histogram for U of T. It was a hard test, there's no doubt about it, and I think the material is a little harder when you're doing things with conservation of energy, conservation of momentum. I still think this is a good result. I am, I'm happy. Though, now, there was a bit of a curve, but I'll tell you how I did it. I didn't want to do just a bump up of 5%, because I wanted to get it up to around 62. What I did is we did a sort of a merit-based curve. So I looked at the multiple choice questions, not me, but Brian and Carolyn and I sat and looked at the multiple choice questions and figured out some of the distractors, the wrong answers, were kind of more wrong than others, like really, really wrong. Like you could just, for example, that center of mass of the quarter circle, one of the choices was, two choices were completely outside of that object, which really didn't make any sense. Whereas two of the other choices, you had to do some work. So I do feel like when you're doing a multiple choice test, I think it's good to cross out the ridiculous distractors, the ones that are absurd, so that you only have left to choose from the ones that you have to do some work, so that if you're rushed in the last second, you can guess one of the ones that at least are not absurd. So we awarded +1 point, so half credit, if you got one of the less wrong answers than the more wrong answers. These single points are by professor's discretion. The choices are not going to be changed. We've made this decision. It's sort of like a little bonus to try to boost up the mark. We're not going to justify why this is a 0 and this is a 1. They're all wrong, but we're giving 1 for things we think are less wrong. The detailed marking scheme has been posted on the portal under course materials, so you can check your mark, make sure it was computed correctly. If there's a discrepancy between the marking scheme and the mark you got, there might be a mistake, so definitely bring it to April Seeley by December 5th and we will correct that mistake. You should be getting the whole thing back in your next practical session. Here's some comments from this morning's pre-class quiz. It's not a very good picture because I only have a black and white printer. Someone just sent this to me, but it's been said, although I don't think this is true, that the 5 p.m. class has more fun, but I don't know. This is a nice big room. Certainly they never saw the giant monkey and the hunter demonstration with the monkey falling from the balcony. Only you get to see that. So anyway, I did dress as a banana for the lecture on Monday. No, definitely not. It was hot and sweaty, and it was a bit of, I think, payback for the midterm or something. But okay. And then, when will we study the study topics for the exam be? So the study topics for the exam is just simply everything. It's a comprehensive exam, a whole course, chapters 1 to 14. Are there any places we can go to get extra physics help? So this is my office hours, it's not just me, but it's also other TAs come to help out. So they'll all get together in one of the lab rooms Monday and Tuesday at 2 and Wednesdays at 3. They'll keep going right through to the final. There is extensive drop-in center hours. That's the physics drop-in center in MP200 right above the lobby, where, like above the Starbucks. There's either TAs from our department, which are grad students, or there's the Vic College tutors who are undergraduates that took this course before and that were really good and hired by me. And there's also your TAs. Your TAs may have additional office hours. This last thing, so for some reason, sometimes, I don't know why, people will, for the Learning Catalytics long answer question, they'll just cut and paste song lyrics. And so, this is a Big Shack song, and the entire lyric, I've just put an excerpt here, but it's the entire lyrics to this song all about some lady who asks her boyfriend to take off his jacket at a restaurant, and then he doesn't take it off, and his response is, man's not hot, never hot, so, okay. I don't understand it, and I don't understand how it has anything to do with the physics, but I just thought I'd tell you that. It's a bit weird, but they still got the 7 points. Okay. Maybe it's not cool to take off your jacket, I don't know. Last time I asked for you to try to tell me what are the forces on the diving board from the support 1 and the support 2. So the way we do this, I'm going to start by actually neglecting the mass or the weight of the diving board for now. We can add this a little later when we talk about gravitational torque. But what you do is you draw an extended free body diagram. Which looks like this. You draw the diving board and you draw all the forces that are acting on it. So there's like F1 acting up, right there. There's F2 acting up. And then there's this 100 newtons acting down. And we still have to balance these forces. So it's not accelerating. Up or down. So the sum of the y components of the forces have to equal 0. So I think what has to happen is this F1 plus F2 has to equal 100 newtons for everything to balance. And then the next step is to balance the torques from all of these. So torque balance requires a pivot. And so you just choose a pivot. Let's do left end. If I had chosen the right end, I would also get the correct answer. If I had chosen the middle, I'd get the correct answer. Since it's in static equilibrium, it's not rotating. So wherever you choose the rotation axis is fine. You usually just choose it so that the math works out nicely. Left end, what will happen is then now you have the torques. Sum of all the torques is equal to the torque 1 plus the torque 2 plus the torque 3. You can call this F3 or something. So these are going to be counterclockwise, so these will be positive of F1 times 1 meter plus F2, that's wrong, times 0. 1 meter. 0 is the distance from F1 to the pivot. Okay. And 1 meter is the distance from F2 to the pivot plus this 100 newtons times 4 meters. So what I get is this torques, which should equal 0 if it's not rotating, is going to be F2 times 1. Oops, this one is clockwise. So you have to minus this. A couple of mistakes here. So minus 400. So F2 is equal to plus 400 newtons. And then you can use this equation to solve for F1. F1 is equal to 100 newtons minus 400. What? It looks like it's actually negative 300 newtons. Which means we drew it in the wrong direction. So in order for this diving board to not fall, you actually need a negative normal force on the point 1, which sort of makes sense, right? It has to get hooked on here by a hook. It has to pull down with 300 newtons, and then push up with 100 newtons, and then down with 100. Sorry, 300. 300. So 300 down, 100 up, 100 down. Makes sense? No, 400. F2 is 400 newtons upwards, and then you've got a F1 downwards of 300 newtons, and it balances out to 100. I said it right, I think. So what I do in these problems is I just draw the forces. If I don't know which way a force is, I just choose a direction. I know it's either up or down, so I just chose up, and then if it turns out in the end, when you solve it all out, that you get a negative number, it means you must have drawn it in the wrong direction. Okay? Okay. It's rather quiet in here. Center of mass. So we talked about this before. It's the average position of all the mass that makes up an object. Center of gravity is the average position of the weight distribution. So they're the exact same thing because it doesn't matter where you put a mass, the force of gravity is the same, it's mg. The only time when the center of gravity would not be the same as the center of mass is if the force of gravity is changing. Like if you're doing an astronomy problem, you're way out in space, and the force of gravity is gmm over r squared. So if different locations have significantly different values of r, then I guess you'd get a different center of gravity. But in our course, they're the same. We talked about this before. But the point was, and I've mentioned this a few times already, when calculating the torque due to gravity, you may treat the object as if all of its mass was concentrated at the center of mass. So if this is the pivot over here, and you want to calculate the gravitational torque, well, you know that in fact gravity is acting on all parts of this object, but you can, I guess, imagine that the gravity is pulling on the center of mass, like if you hook it right there and pulling down. And that's how you find the torque. Because you need to find the points where all the forces act on your extended free body diagram. So, example, if you have a 4 meter long, 500 kilogram steel beam, and it is supported from the right end, supported 1.2 meters from the right end, what is the gravitational torque around the support? So this is, the pivot, I guess, where you calculate all your torques. So what you would do is say that the torque is equal to, you can either say that it's R times F times sine of phi, where here is your R, and here is your F, I guess F down. And so this phi angle here is 90 degrees. Another way of doing this, if you rearrange, it's equal to F times R sine phi. So I like to call this the lever arm. And this is always, L is the distance between the force line and the pivot. So in this case, L equals R in this case. But you'll see me in future problems using this lever arm quite a lot because it's nice and visual. I can always see the lever arm in my extended free body diagram. And then I'm not confused about where the phi is and where the sine of phi is. It's pretty helpful. So anyway, a torque is equal to mg times r, which is, it's 500 kilograms times 9.8 times r here is the 0.8. So I get in my calculator 3920. The units, SI units of torque, turn out to be newtons times meters. And then the vector of tau is equal to 3920 newtons times meters. And then you have to use this, it's counterclockwise, so you can use the right-hand rule, and this is out of the page. Out of page. Do that. So that's how an example of calculating gravitational torque. So moving on, where this comes up a lot is in static equilibrium problems. So, true equilibrium, for static equilibrium, means that it's not moving, which means that it's not accelerating either in the y direction or in the x direction. And in addition to that, it doesn't have any angular acceleration. Here's a picture of a crane. It was all set up, and then there was a net torque around its far wheels there, and so it had angular acceleration. So it was not in equilibrium, and it crushed the house. And I really hope that nobody was hurt in that, and that somebody got sued and the insurance companies paid up. So, for a rigid body in total equilibrium, there's no torque about any point, and so there's actually three equations that you can use. You can solve for up to three unknowns. They're on the bottom there. No net force and no net torque. So you've got the sum of all the x components of the forces equals 0. The sum of all the y components of the forces equals 0. We used that actually in the diving board example. And then the sum of all the torques equals 0, and this is the one that comes up quite a lot. But it's good to keep these ones in mind because they might just be the equation you need to get that next unknown. So, steps. You draw an extended free body diagram. Same as the old free body diagram, except now instead of a point, you have to draw like a box or something, or a big circle, or it doesn't have to be a beautiful diagram, but just something that shows where the forces act as well as what direction they're in. Then you have to, of course, define your x and y axes, and you have to choose a rotation axis. And it's not rotating, so like I said, it doesn't matter where you choose it, but all of these choices should be done to simplify your calculations. Then each force will have an x and y component and a torque, although some of these will be 0, hopefully. The more zeros you get, usually the easier it is to solve everything. And you sum all these up and just set them all equal 0. So we've got it. Let's do I'll write it here. Learning Catalytics question. For you. An object could be in static equilibrium when A, only one force is acting on it, B, two or more forces are acting on it, or C, only one torque is acting on it. Only one of these is correct. I'll give you 1 minute. Yeah, so you can't have something in equilibrium if there's just one force acting on it. A good example of something that has only one force acting on it is this tape right now. It's accelerating. The only force acting on it as it's flying through the air is gravity. In every other case, like the tape right now, when I put it on the table, there are two forces acting on it, gravity and normal force. And it's in equilibrium because those two forces cancel and all the torques cancel as well. So a lot of people this morning asked me to go over this question. A 20 kilogram uniform plank. This is a pretty difficult pre-class question. 62% of you got it though, so that was really good. It's asking you to practice all this stuff. So let's go through it. Let's call the plank M1 is 20 kilograms, supported by the floor at one end and by a vertical rope, some tension we're trying to find on the other. And it's at some angle, which we might as well call theta, I guess. A 50 kilogram mass person, so here's your M2, equals 50, stands on the plank a distance 3/4 of the length of the plank from the end to the floor. So let's say length is L, length of plank. So this guy is pushing down with M2G. And then at the center, since we assume it's a uniform plank, there's this M1 times G. M1G down there, and then there's some normal force upward on here. So this is your extended free body diagram of the object. I've drawn all the forces I can think of, and I've drawn them at the places where they are acting. So, you can say that the sum of all the Fy forces is going to be the normal minus the M1G minus the M2G plus the torque. Sorry, the tension all equals 0. The problem here is that N and T are unknowns. So you can't really solve this just using the force equations. You don't know what the normal force is, and that's going to be end up what's setting the torque, the tension. So you have to use torques. So what I like to always do in these problems is check to just see if the old equations will work. Okay, it didn't. So let's use torques. And let's define, I don't know what the normal force is and I don't care about it, so let's define the left end to be the pivot. And that way, the normal force won't have a torque. So you'd say that the sum of all the torques is equal to the torque due to the normal force plus the torque due to mass 1 plus the torque due to mass 2 plus the torque due to the tension. And the other thing I'm going to do is calculate all the lever arms. So this is, I guess, R2, and lever arm for R2, if this is theta, L2 is equal to, I guess, L over 2, which is the R2, times cosine theta. Now, the cosine thetas aren't going to matter, but basically I've got the normal force times 0, because the lever arm is 0, and then this is going to be a clockwise, so actually I have to subtract it, of the M1G times that lever arm, L over 2 cosine theta. And then the person is going to be M2G times, I think it's 3/4 of L times cosine theta. And then finally the tension, which is the only counterclockwise positive torque, so tension times L times cos theta. And set all that equals 0. And so there's a bunch of things that we can then cross out. N times 0, 0. And then I'm going to divide both sides by L and divide both sides by cosine theta and try to simplify this thing out a little bit. I got 0 equals, there's a 0, there's a negative m1 times g over 2, and then there's a negative m2g, and there's a 3/4. And then there's a plus the tension. So the tension just equals m1g over 2 plus 3m2g over 4. So it's equal to 9.8 times 20 over 2 plus 3 times 50 divided by 4. So I got 465.5 newtons. And that was correct. But you can round it to 466. Okay. It just takes some practice getting used to all these things and trying to figure out where to do your lever arms. I think I'm just going to keep going and scanning these. So I was asked a lot about this ladder this morning. Can you solve the ladder? So should we solve the ladder? A 3-meter long ladder leans against a frictionless wall. I don't know if, Kevin, can you dim the lights a bit so there's more just in the front of the room? So there's more contrast on the screen. Leans against a frictionless wall at an angle of 60 degrees. What is the minimum value of mu sub s, the coefficient of static friction with the ground that prevents the ladder from slipping? So you have a frictionless vertical wall, but you have a friction-y horizontal floor. And you're asked how much friction does it need so that the whole thing doesn't slip out? You can imagine what it wants to do. You guys okay with that? So you can still see what you're writing on. I think it's okay. It wants to go like this. And so here is this extended free body diagram that I've drawn here. And what I'm going to do is start with the torques. So I'm going to choose the pivot equals the base. And I don't know, you can choose it wherever you want, but to me, it feels like it wants to rotate around that point, so I think it's a nice point to choose torque. But you can choose it up here, it also works. You can choose its center of mass. But in this case, you're a normal force 1, so there's 2 normal forces, one from the floor and one from the wall, and your static friction both have 0 torque. So that's nice because their lever arms are 0. And then N2 will have a clockwise negative torque around that base. And so I think if N2 was the only force acting on it, it would push this way. It would make it go clockwise. So it's a negative torque. And there's got to be a positive torque somewhere. Well, yeah, it's probably going to be this Fg, the gravity force, is going to be a counterclockwise positive torque. Okay? So if gravity was the only force, it would pull the thing down like that. And so the torque due to Fg, let's do these in sequence. The torque due to the normal force is equal to negative N2 times your, I guess, lever arm 2 is equal to negative N2 times L times sine of 60 degrees. Okay, that's going to be this distance right here. This is your D2. That's your kind of lever arm of N2 through the distance from the force to the pivot. Wrong. Distance from the force line to the pivot is D2 down there. Better. Yeah, it's already drawn on here. And then the torque due to the gravity force is going to be the m plus m times g times, I'll use d1 here. This is the distance between the force line for gravity and the pivot. And it's going to be mg times L over 2. Since it's a uniform ladder, the center of mass is halfway, and now there's going to be a cosine 60. And so the sum of all the torques, the net torque, which is going to be equal to 0, is going to be the torque due to N2 plus the torque due to the gravity force, which is negative N2 times L sine 60 plus mg L over 2 times cos 60. So N2, you can find out from there, is equal to mg times L over 2 times cos 60 degrees divided by L times sine 60. Okay, so that's about as far as we can get with that. And the next thing I'm going to do is I'm going to balance the x forces. So let's balance the x components of the forces. And so F net in the x direction, which is 0, is going to be N2, which is pointing to the right, minus the static friction. Okay, and so that implies that this static friction, whatever it is equal to N2. And then we can balance the y forces, and we say that F net in the y direction, which is equal to 0, is equal to N1 up minus mg. And so N1 equals mg. And then we know that Fs max is equal to mu sub s times N1, which is mu sub s times mg. And then we set this equal to Fs, which we have because we solve for N2. So we say that mu sub s times mg is equal to mg times L over 2 times cos 60 divided by L times sine 60. Make sense? I've got 3 equations, 3 unknowns. I've sort of plugged them all in. And now I've got an equation for, actually there's an L on the top and the bottom. And I got mu sub s is equal to cos 60 divided by 2 times sine 60. 0.29. That's going to be the minimum coefficient of static friction needed so that the thing doesn't slip. Because I've set the Fs max equals to the static friction. Okay? We can get a little involved with these questions. Okay. Next, I want to talk a little bit, next 15 minutes, about stability. So, the location of the center of gravity is important for stability. If we draw a line straight down from the center of gravity, it has to be inside the base. So here's the Leaning Tower of Pisa. The base is right down here. Base. That's what's supporting it, so there is normal force that can be provided from the ground upward at any point on the base, and that can be any amount. If the center of gravity is directly above the base, then it's in stable equilibrium. If the center of gravity is outside the base, then the thing falls. And so let's deliver another Learning Catalytics. We look at these 3 trucks. And it asks which truck or trucks will tip over. And you don't know how all the boxes are piled in the back of these trucks, but you do know that it's hard to see these X's here, the center of masses are here, here, and here. So this is the center of gravity of all of these trucks. So they're loaded in different ways. So try to, from that, determine which one will fall over. I'll give you a minute to think about that, which one it ones. Yeah, so I think it's only one of these. So if you, I guess it's a bit of a judgment call. I think this one is outside the base. This one is sort of inside the base, and this one's definitely inside the base. It's just a question of, is the center of mass over the base? So there's a normal force upwards on this left tire, which is self-adjusting, so that it always can provide an opposite torque to the gravitational torque, unless it's here. In this case now, here's the pivot. Well, wherever you put the pivot, both the gravitational torque and the torque from this normal force are going to be in the same direction if it's pivot here. It's going to tip over. And while we're at it, I want to do this silly question. I don't know if this is going to work or not, but just out of curiosity. So, I graduated from U of T in '93. So can you just type 93? I'll just give you. I'm going to put this timer on 30 seconds. Some people put it anyway. Okay. Just silly. Okay. So, next thing I want to do is consider a block of length L, and it's hanging off the edge of a table. How far off the edge can I hang it before it falls? So we'll do the demo twice. So first one, and he's labeled the half point. If I keep on pulling, more and more and more and more, whoop, it tips when the center of mass, which is right at the line, goes off the edge. And the closest I can get it is put the center of mass right on the edge. Oh, it doesn't. Try it this way. If it's drawn exactly right. But if the center of mass is directly over the edge of the table, then it is stable. If it goes beyond, then it falls and is unstable. So, oh look, I have both. Okay, let's just keep it like that. So, it's like this. And I think the way I would put it here is if you define this to be x, then you'd say x equals L over 2. Okay, because the center of mass, Cm, is directly over edge of table. And then the next question is, what if you stack another block on top of that block? Two blocks have length L. The top one is hanging a distance L over 2 off the one below it. So you know it won't fall. How far off the edge can the bottom block be before the entire stack topples over? So this is a bit strange. What I'm doing now is I'm putting a block here somewhere, and I don't know this distance x. And right on top of that, I know that I have this thing, some distance L over 2. Can you picture that? And so you solve for x. So what I'm going to do is put the center of mass of both blocks at the edge of the table. And so what I'm going to say is I'm actually going to say that this is the origin. That's my clever trick. And then I'm going to say that x, center of mass, is equal to, this is the top one, so 0, because I've defined that to be the origin, times m, I guess. And then plus this one, which is going to be trying to figure this out here. XCM. Oh yeah. the distance to this center, so that's the center of mass of that block, and this center of mass of that block is L over 2, plus L over 2 times that M. Make sense? I'm adding these two objects. And then divide it by the total mass. And so I get L over 2 times M divided by 2M. So I get X is going to be L over 4. There's a bit of a trick there. So there's two objects. This first one is the top block, and this one is the bottom block. And in both cases, I've measured this distance from the origin, which I've defined to be here, to the center of mass. And then we can do it for more and more blocks. 3 blocks. Top one is hanging this distance, so and here you use the result from the previous one. So I know that now this is, so this is again is X, and I'm putting the center of mass of all these things directly above the origin, and then finding out how far this last one is, and this is L over 2. So center of mass of these is above origin. And so X, the whole thing, is equal to 0 times, I guess it'll be 2M, plus L over 2 times M divided by 3M. And you get that X equals L over 6. Okay, and then with 4 blocks, you get X equals L over 8, 5. You get X equals L over 10, etc. And what's really weird is that if you add a half plus a quarter plus a sixth plus an eighth, that's a harmonic convergence. So you can add up to any number. It diverges. And so you can have them hanging off as far as you want, and it doesn't topple over. So you can try it here. There's a half. How far can you hang this? Wait a second, got it wrong. Half one goes on the top. You line that up with that one. And then you do a sixth, okay, and you do an eighth, etc., etc., etc. Oop, is that right? No. Like that. Quarter. Like that. Okay, the whole thing is sort of stable. And so, and if you keep on stacking enough blocks upwards, it can go out to infinity. Okay, so it's kind of weird. Doesn't fall. Oh, actually, we can go further, right? That's your maximum overhang. That's better. Okay. What time is it here? Yeah, I had a couple more things. This is just about stability. So again, an equilibrium is stable. Well, actually, an equilibrium is stable, and this is going to be important for simple harmonic motion, if any little force, slight disturbance, will be restored. And it's unstable if a slight disturbance causes it to move away. And so there's different kinds of stability. I'm actually not going to do it, there's not enough time. But this is neutral stability, so I won't ask it on Learning Catalytics due to time. But neutrally stable means that if you disturb it a little bit, it just goes a little bit and doesn't accelerate. Stable means that if you disturb it a little bit, it always comes back. it'll kind of oscillate around the middle in simple harmonic motion. Unstable is like you're at the top of the hill. If you give it a little nudge, it's unstable, then it will accelerate to infinity. And then there's something that Wolfson calls metastable. I guess this is sort of subjective as to what's metastable and what's stable. But it sort of depends on how slight the nudge is. If you give it a big enough nudge, it'll go over, but otherwise it'll stay in that little zone. It's again kind of subjective there. Usually you just talk about stable, local stability, or local instability. So I do hope you have a good weekend. And here's something to think about. So the next step here is simple harmonic motion. We're getting into oscillations. And idea. If you have a mass on a spring, and you stretch the spring, and then release the mass, it's going to be pulled back towards equilibrium. My question is, when it gets to equilibrium, will it be at rest, or will it be moving? And if it is moving, in which direction will it be moving? And I'll talk about that on Monday. Have a great weekend.